Good day to everyone. Thank you all for finding the exida webinar on getting credible failure data for SIF design verification. Today we're going to be talking about basically getting good, credible, realistic failure rate data to use in safety instrumented function design verification. That's the essence of what this is all about. Let me just note that you will be getting a copy of these slides and that I'm happy to take questions at any time during the presentation. I will try to keep track of the questions bar and look for them at the right time. All right, let's go. What's credible data? Why do we need it? Where do I find it? My name is Bill Goebel. I was one of the co-founders of exida back in 2000, and I'm quite proud that exida has grown to be a relatively large global company with offices around the world. We specialize in functional safety, alarm management, and cybersecurity. One of our business groups does engineering tools. We have two tool suite, Excellentia, which is a tool designed for safety instrumented function verification. And it comes with a full set of data, which we have already, as I will explain, we have verified against field failure data. There's another set of tools called OEMX, is for product developers, both mechanical, electronic, and programmable electronic systems. In terms, another business group does product certification. I hope you've seen our many certificates out on the market. We're pleased how, again, I'm also pleased how far exida has come in terms of market leadership in the functional safety certification business. exida is very technical. We do a lot of research. Relevant to this webinar, we do a lot of research in field failure rate data. We use it to help calibrate our failure rate predictions. We publish our methods and our data in books, white papers, and of course, present information in webinars. We do charge money for our data books. It helps us pay for all these white papers and all these webinars. Why is there any interest in credible, realistic failure rate data? I think we are quite blessed with a second generation set of functional safety standards that have implemented what I've come to learn is an ingenious method for managing risk. It all started with ISA SP 8401, a standard released in 1996, where step one, for every hazard in an application, a risk reduction need is determined in a process hazard analysis. That can be quantitative, it can be qualitative, it can be a target risk reduction number or a SIL level. Kind of a nice arrangement, order of magnitude SIL levels with, if you wish, more precise target risk reduction factors. Then, given that as a requirement for a design, an engineering design process proceeds with a defined level of rigor, testing, and so forth as a function of SIL level. We calculate performance metrics, in particular probability of failure, and we try to specify operations and maintenance requirements that vary with the SIL level also. This whole approach is called performance-based. There are no cookbook designs in that standard. The standard doesn't tell you how to design, which is pretty good. If you know how to design, you can optimize, you can make trade-offs between capital expense, operating expense. You can use new technology, which is rapidly occurring in the marketplace with the substantial expansion of functional safety across so many industries. A performance-based approach, as I said, does not provide a cookbook on how to design. Instead, it says you design what you think is best and check to see that you meet what we call 3 essential performance metrics, the 3 barriers. And of those 3, it's my belief that the hardest and sometimes the most confusing is barrier number 2, calculating a probability of failing dangerously. What is the probability that this safety function you have designed will not provide protection when a hazardous condition occurs, when a demand occurs? That's what we wish to calculate. Now think about that for a minute. How in the world would we do that? Well, the bottom line is we use the science of reliability engineering, and it has been well developed over the last 6 decades or so. Methods, formulas, techniques have all been created, but all of those methods, techniques depend on good input, which comes from a number of variables, but the variable that's generally acknowledged as most important is the dangerous, undetected failure rate. And what does that mean? Well, if you have a dangerous failure, your safety function may not protect you if there's a dangerous condition, and there are no automatic diagnostics that can detect the failure. That's kind of bad. Think about it. That's really bad. We don't want DUs. Ideally, we'd like that number to be 0, but the cost of perfection, I've heard someone say, the cost of perfection is infinity, and we can't afford that. Therefore, we have imperfect devices that have failures we can't practically eliminate. Many cases, they're unknown to us at design time. So we will have DU failure rates in the different devices we use in our safety instrumented functions. But it is absolute, and it is, I must say, and it's absolutely possible to have good, credible failure rate data if the person performing the safety instrumented function verification calculations makes certain that the failure rate data is intended for the specific application and environment, is from a credible source using credible methods, and matches the site, and the failure rate data matches the site operation and maintenance capability. I know that sounds kind of weird. What did he say? Site operations and maintenance capability. You know, a lot of reliability engineers have never thought that the failure rate of a particular manufacturer model number device changes from site to site, but it does. I have a lot of failure rate data that shows this. And at exida, we have created models for how to measure and model your site operation and maintenance capability. That's all part of the Excellentia software. And the failure rate data used by Excellentia does account for different site operations and maintenance capability. if we go back to our standard, and I love the ingenious method that allows optimization, but that optimization, the calculation of our primary performance-based metric, depends on credible, realistic failure rate data. Well, where's failure rate data come from? There's a number of sources out there in the world today. Some of them have been around longer than others, but there's the B10 prediction method, the manufacturer's warranty data, which was a key way of doing things decades ago. There's plant data gathered up by particular sites, and consortia data, where particular sites aggregate data to come up with hopefully more accuracy. And there's the FMEDA data prediction method. Any one of these categories can have problems or can produce really credible, realistic results. Where do these problems come from? 3 primary categories. Data censoring, data filtering, invalid assumptions, and invalid analysis methods. I once met an engineering manager that worked for a manufacturing company, and he said, "Don't tell me about this failure rate data business. I can hire a statistician to give me any answer I want." Now, we have no interest. Go away. Not in those words, of course, but, and I thought to myself, how in the world could a statistician come up with any answer they want? And I realized, aha, by making different assumptions. Oh my. So let's take a look at these categories and take a look at each of these sources. I'll deal with the B10 pretty quickly. It's a method that comes from primarily the machine safety people. And it's really a mechanical wear out test that was done years ago just to predict useful life. And it assumes that, but they're trying to use it to predict random failure rate during the useful life. And I've never really seen any theoretical basis for this. If you have a theoretical basis paper and this is explained, please send it to me. The bottom line is, I remember discussing this in grad school, and everybody concluded there's no way this could ever do an accurate job, primarily because of the invalid assumption that failures during useful life are premature wear out. That's just not a valid assumption. There are many, many other causes for failures during useful life. So we throw that method out the door. Manufacturer's warranty data. Now, a lot of people think, oh boy, this is a great way to do it. And other people think, no way. How's it work? Well, manufacturers have shipping records. They can estimate operating hours, but they don't really know. And they get failure reports recorded from customers. Now, this is a sanitized set of real failure rate data on an electronic assembly. I see over a 3-year period, they had 188 failures. And you can see that they have a pretty large quantity of operating hours. Well, but I was like, well, do we use 188 as the number? And most manufacturers say, no, 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 no. I was taught never to use that number when I worked for a manufacturer. Most manufacturers assume that their incoming inspection test will detect whether a failure has occurred or not. And so they would immediately eliminate all the no fault found or the no fault found failures. So they would say, no, it's not 188. We're going to immediately subtract 48 of those. But that assumption that their incoming inspection can detect every field failure is weak at best. Some are better than others, but that's a bad assumption in general. And there's more. Some manufacturers say, look, I only count failures caused by manufacturing defects. All the stuff caused by the end user is not really our fault. It's their fault. Therefore, it's not a failure. I know that sounds crazy in many ways, but that is exactly what I was taught also when I worked for a manufacturer. And the manufacturers then will begin saying, aha, that's not a failure. I've got to get rid of this one. I can get rid of these. This is not a failure. These are all, oh, okay, I have to take credit for the faulty components and the manufacturing component loose issue, but I can get rid of all the rest of these because they are just not failures for my definition. That is what I mean when I say data censoring and data filtering. You make up an excuse, define failure differently than reality, and cut the number down. In this case, if all those failures were excluded, I would have a number of 62 failures instead of 140, 62 instead of 188. That's about roughly 1/3 the failure rate. And I haven't even thought about the assumptions of how many units are returned, what percentage is returned, and what are the real operating hours. So it's more likely that the result of this is an order of magnitude less than reality. So in general, this is a method that is not credible. However, there's still a lot of valuable data here, and the number of 188 could be used if we had a list and we could include all these other failures, and we could calculate, we could come up with some less optimistic assumptions, and we might have a lower bound failure rate that can be useful, and I'll explain how it's useful a little bit later. Now, there are many operating industrial plants who collect failure rate data, some better than others. And there are consortiums where a number of different operating companies aggregate their data. And that sounds pretty good because that's real field failure data. However, they still could have serious problems with data censoring and data filtering. They still could be making invalid assumptions, although generally speaking, they don't really have invalid methods because most of the plant people and especially the consortia use very high quality experts to analyze the data. But some problems can still occur. Take a look in the lower right-hand side of the screen. One consortium, Nemor, a group of chemical industry companies in Germany, wrote in a recent paper that valve failures or failure rates are so low that the values can be neglected in PFD calculations. And I read that and say, oh my goodness, where does that come from? And I've got a little bit of an insight into that because some of our people went and visited a number of Nemor members and talked about how many failures they had and how many they reported. And in one case, the plant or the maintenance engineer manager said, we had 9 failures, but 7 of them were systematic, and therefore we're going to follow 61508 and we're not calling them a failure. Only 2 were real failures. Oh my goodness. Well, hold it. But if were those failures that where the safety function would not protect you if there was a dangerous condition? And they said, oh yes. Well, then they're real failures and you should count them. Oh no, they're systematic. Anyway, another consortium, ORIDA, the Offshore Reliability Database Association, collects data from a number of operating companies. And they are the people that convinced a number of us from exida that you should count every single failure that actually would prevent the safety function from protecting. ORIDA counts all of it. They do not censor the data. ORIDA, we were lucky enough, one of our outside consultants was lucky enough to get the opportunity to study the raw failure reports from ORIDA, and did some very careful analysis on a homogeneous set of data on valves. And you can see the result. The mean failure rate was 666 fits, which is 666 times 10 to the minus 9 per hour. The 85% upper confidence limit was 1,850 and the lower limit was 155. All of those numbers are easily categorized as cannot be neglected. If you want to see all the derivation and all the math, there is a white paper on the exida website. We tell you exactly where all this information came from and how the calculations were made. The really great thing would be, FMEDA data prediction. That's the fifth technique. Failure mode effect and diagnostic analysis. This is a technique that was created in the late 1980s, specifically to predict failure rates for newly designed devices where there was no field failure data available. Now, that's not anything new. There's a number of standards out there at the time that showed how to do that, total failure rates, but how do we get this FMEDA to be accurate and realistic and therefore credible? Well, you have to create a component database, which you see in the upper left-hand portion of your screen. And the FMEDA technique, if it has a good database, can predict failure rates and failure modes, diagnostic coverage, and useful life in a very realistic way. And I'll explain that in just a bit. If FMEDA works properly, an FMEDA prediction should match the field failure reports. They should match up perfectly. What if they don't? And well, the method we've developed at exida we call calibrated FMEDA. And in order to ensure we're producing realistic, credible results, the component database is calibrated against quality field failure data. And I mean no data censoring, realistic assumptions, realistic, accurate methods used on homogeneous data. We get that data from manufacturers because it can be used as a lower bound if you make realistic assumptions. We get data from the exida tool SILSTAT, which is used by many operating companies around the world. We get data from specific end users, and we are very lucky to get data from ORIDA they are most willing to share to improve the safety of the world. We get the data from field failure and we compare it to the FMEDA data, and they should match. If they don't, we investigate why, and sometimes we update our database, and sometimes we find the field failure data is censored or something. Or sometimes we even find some significant design flaws in the product and tell the manufacturer how to do a better job. Some certification bodies, including exida, use the calibrated FMEDA prediction method. And at this point, it's based on over 400 billion unit operating hours of field failure data. Field failure, that allows us to provide a lot more detail. Note on this one certificate, you can see different failure rates for different applications, different environments, and for SSI too. Now, how do you validate failure data? And you should be validating everyone's failure data, including exida. First thing we're going to look at is if you have some B10 cycle database, don't take much time. Please throw it away immediately. I can only imagine some very rare circumstances where the data would be valid. Manufacturer's warranty data is also typically highly optimistic, and designing with it is just not realistic at all. All other data, industry databases, FMEDA is done with consumer or military component data, and industrial databases need to be checked. And you need to say, all real failures counted? Are operating conditions similar? Are the environmental conditions similar? And is the application similar? And you should check it against a website called SIF data. I'll give you some examples. What is this SIF data? Well, SIF data was published by exida. There's no charge for it as a service, so people could be checking the credibility of their data. Starting with over 400 billion unit operating hours of data, we created a component reliability database. We used that to generate FMEDA results, and we combined that with ORETA data. We looked at chemical industry data, power industry data we got, and we did a statistical analysis of the FMEDA results. That shows the fundamental difference between different designs. Different designs where the failure rate would be aggregated to make the average. This is what SIF data looks like. You can see for categories like pressure switch, pressure transmitter, safety certified pressure transmitter, and so forth, there's a dangerous undetected failure rate in FITS, low bound and high bound. Now, sometimes the numbers are pretty far apart, like on a pressure switch, but the designs, the different designs on a pressure switch are significantly different. And we have that data. And so we've at least given you upper bound and lower bound so you can check credibility. And for the most part, it's the lower bound number that really counts. There's a lot of data for, I'm just giving you samples. There's a lot of data for a lot of different type of devices, including a number of valves, even down to the application, close on trip, open on trip, or the environmental requirements or performance requirements, I guess we should call them, for tight shut off or not. And the failure rates, as you can see, are quite different in a floating ball valve for these three different categories. Tight shutoff is tough. It's easy to scratch the ball or scratch the seal and violate tight shutoff requirements. That's what SIL-safe data is. Now, let me give you some examples of how it works. Let's see if it helps us any. A mechanical manufacturer of an actuator, spring return actuator, has published a set of data based on something, and the lambda D is 17.3 fits. Wow, that feels kind of low. I went through the report a couple times, and there's no information about the assumptions and the methodology, but I'm guessing it's based on manufacturer's warranty return data with assumptions similar to the ones I made when I worked for a manufacturer. Let's look at SIL-safe data. This is, that's a Scotch yoke actuator. It's not double acting, it is spring return. So the number should be between 400 fits and 1250. It appears clearly as if all real failures were not counted, but we just don't know. It appears as if operating conditions, we don't know anything about them. The only thing we know about the application environment is pneumatic or hydraulic. No, they don't even give us different numbers for pneumatic versus hydraulic. We checked it against SIL-safe data and discovered that is so far from being credible. Please don't even think about using that kind of a number. Let's look at a certificate. Some certificates are good, some aren't so good. This certificate uses the calibrated FMEDA method. That method, which is based on field failure data, does count all the real failures. It provides different failure rates for different operating conditions and different environmental conditions and different application conditions. And we can check it against SIL-safe data. Let me see, the spring return pneumatic actuator has a DU of, there it is, 427. Okay, let's look. Oh, it's within limits for a pneumatic Scotch yoke spring return actuator. That one's kind of toward the low end, but it's well within limits. This one is absolutely credible. Let me look at another certification body report. This report is giving failure rate data for floating ball valves and trunnion ball valves. But I looked at the comments and they said all calculations, okay, field experience, that's good. Confidence level of 90%, that's good. Somebody's doing work that knows what they're doing, in my opinion. But the CB has not verified the accuracy or the correctness of the field experience provided by the manufacturer. The manufacturer provided a document saying it's accurate, but we don't know what the assumptions are. We don't know if data censoring was used. We have no, in fact, it looks very much like all real failures were not counted. We don't really know much about different operating conditions. We don't know whether the numbers are applied to close to trip or open to trip. We don't know whether it applies to a severe service environment or clean service. And we just don't know if the application requires tight shutoff or not. None of that information is provided. So let's check it against SIL-safe data. The floating ball valves, the upper limit of the dangerous failure rate is 11.6 fits, 11.68 e to the minus 9 failures per hour. And for the other trunnion or floating ball valve, it's 25.5 fits. Whoa, those are low numbers. SIF data says it really should be between 300 and 900. How about the trunnion? These numbers are 95.1 to 200. A little closer on the upper limit, but to the SIF data, but it's not even, it's just not there. This data is absolutely not credible. And so we don't know if it's warranty data, but it looks like it is. And this is exactly the kind of stuff you see in manufacturers' return warranty data. Here's another one. The data for two types of ball valves are presented, trunnion and floating. Now this one came up with a number of 210 for trunnion and 109 for floating. Well, it's not as ridiculous as the last one, and the methodology used is completely statistically valid. But it's important we note the warning given by the analyst. And I clipped it out. It's kind of small print in the report. The stated values are field failure feedback from the last 5 years, random and systematic, whatever that means to them, which are the responsibility of the manufacturer, were examined. I applaud them for telling us exactly, telling us that they have done a lot of data censoring. The concept of manufacturer-only failures being valid means that a site has perfect operations and maintenance and never, ever makes a mistake. I don't think that's very realistic myself. I sure make mistakes. The method shows technical validity, and the certification body was quite honest and forthright by telling us about this problem. But we know that all real failures were not counted. They only gave us one set of data, so we don't know about operating conditions, environments, or application. And let's check it against SIF data. Oh, way below limits. This data is not credible, primarily due to invalid assumptions, which might include data censoring and which likely include data censoring and data filtering. Here's another certificate. It's based on a calibrated FMEDA for what's it for here? Let's look. Do you have trunnion mounted ball valves? And we have 505 fits for a full stroke clean service to 898 for a full stroke severe service. What's severe service? I think if you look it up in the FMEDA report, it'll tell you it's a corrosive process material, an abrasive process material, or combination thereof. Are all real failures counted? Yes, they are in the calibrated FMEDA method because the calibration is based on real field failure data. It does give you separate data for operating conditions, operational environments, and applications. And you can see that. There's full stroke, tight shut off, or open on trip. Full stroke means close on trip. Clean service, or severe service. So there's 12 combinations of different application categories and operational environments. Now, I know in the FMEDA report that it stated that all calibrated all the data on this certificate is for what exida calls SSI equals 2, which is the average operations and maintenance conditions. Let's check it against SIL-safe data. Trunnion ball valve, we have a number between 505 and 898, depending on application and service. Fine, that's well within the range. 898 is getting a little high, but closed to trip, how about, that's not bad. I think this information is absolutely credible. How about floating ball valve? Well, all real failures are counted. The operating conditions, environmental, and different applications are all provided. Let's check against SIL-safe data. For the floating ball valve, we have between 369 and 693. SIL-safe data has 300 to 900. That's good. It's in the range. Yeah, that's kind of mid-range. The best is, what's the best on here? Full stroke clean service. Yeah, I guess that makes sense. Clean service does not cause as many failures as severe service. Full stroke closed to trip is a very common application. This data is credible. If we look at it, what we see from these three examples and the calibrated FMEDA is that a number of them don't quite meet the requirements. One of them, example number one, is what I would call egregiously low. That is ridiculously low. But that's the kind of stuff you get from manufacturer's warranty return data. We conclude that statistical estimation techniques based on the manufacturer's return data may have optimistic assumptions where the results are likely very inaccurate. In other words, low, because manufacturers want to use this to tell you that they're the best company in the world. That's what I was taught to do. And the numbers don't change even if they're accepted and published by a third party or even a certification body. Some certification bodies, however, use field failure data via this calibrated FMEDA process, and this data will meet realistic criteria. Now, at exida, we publish our results, we publish our methods, and I've given you 5 references on how we compare primarily mechanical components, because that's where all the controversy is right now. I can hear that. I can hear the sentence now. Field failure data for mechanical assemblies can be neglected in SIF verification calculations. Oh my. Now, what do you do when all the data available for the devices you are using is not credible and realistic? Well, I recommend you use a mid-range number from the SIL-safe data. I just pick the middle number, take the average between the high and the low, and use that as your generic failure rate number rather than 17.3 fits, for example. I'd like to conclude that I'd like to remind all of you that any engineer performing SIF verification calculations has the duty to verify the given data from any source. The verification must check applicability of the data. Is it a functional match? Is it an environmental match? And number 3, the verification must check if the data is credible help yourself to SIL-safe data and add in a good dose of engineering judgment. If you'd like to know more about this, let us know. We have other webinars coming and lots of white papers. And even this material is covered pretty thoroughly in one of our books for mechanical parts, Final Elements, by 3 of people that were working for exida. Anybody have any questions? I'd like to hear them.
All right, Bill, we have a couple of questions here. Our first question, would you please elaborate on B10?
Oh, I could complain about B10 for hours, but it's a cycle test for mechanical, designed for mechanical devices, where you run them as fast as you can until 10% fails. Then you use a small formula from, I've seen it in ISO 13849, but the assumption made, unstated by the way, and I'll just repeat, is that all failures during useful life are due to premature wear out, because in fact, many other failure modes and failure causes exist. So just because you run something up and down and you count the number of cycles before it fails does not give you any relevant information about the failure rate during useful life, because those tests are typically run in a laboratory under laboratory conditions, and they're usually run at high speed because it takes a long time to run many parts, to cycle parts enough to cause a failure. I hope that's enough for now. We do have a white paper on this subject, which is roughly the same title as this webinar, getting good failure data. Another.
Our next question, since calibrated FMEDA data is gathered from different sources and calibrated with the FMEDA, do you think that the calibrated FMEDA data sometimes can be overestimated? Overestimation is better than underestimation, but still we should get the max realistic criteria. Your thoughts on this, please.
Oh yes, you should get the max. The bottom line, and it's good and bad, is that the calibrated FMEDA data is average. It's not overestimated or underestimated. In fact, as you can see, if you read our papers, comparing field failure data to FMEDA predictions, the FMEDAs are hitting right in the middle of the statistical range, average. The FMEDA predictions are, initial predictions are defined for site safety index equals 2, which defines average operating and maintenance practices. Now, exida does have a model for 5 different levels of operation and maintenance capabilities with correction factors built into the Excellentia tool. And the FMEDA predicted data goes into there, so you can adjust it to your actual site safety index. If for some reason your stress conditions at your site are stronger, or the stress is higher than average, you will get a higher failure rate. And that's why it's a very good idea to continue to gather field failure data on your own so you can adjust for your particular site. Right now it's average, and it's coming amazingly close to the average of the field failure data. You can read about that. We've done a lot of comparisons over many, many years. Do you have any more, Kristen?
I do. How would you deal with user logged faults which fall outside SIF data ranges?
Well, there's two things I would suspect right away if I saw that. I have seen that. And what I discovered is that the site, the operations and maintenance practices were not good. And if you lower the average SSI2 down to an SSI1, the predicted or the calibrated FMEDA failure rates will go up. And if you lower it to an SSI0, they'll go up again. And it's significant because the field failure data indicates a lot of the failures are caused by bad operations and maintenance. Oh, I have many stories on that. I chuckle a little bit, but they're actually very sad. The other situation that I've seen for a high failure rate is due to a design flaw in the device. We usually can find that right away when we're doing, as soon as we get good field failure data on a new device, we may discover that the numbers indicate higher failure rate than we have predicted. And in several cases, we have discovered by digging in and doing root cause analysis that, excuse me, we've discovered that there's a design defect that is responsible for the failures. I have several stories on those, but they're all documented in one of our white papers as well. So those are the two primary reasons we have seen for that kind of result.
If our experience on site is that the ball valve has not failed in 20 years in specific service, can we adjust?
One valve, statistically, you need about 10 million operating hours to make adjustments. If you had, let me think what they had on Narita. They had a specific manufacturer model number, and I think we had 77 valves on site. And they gathered data for, I can't remember the number of years now, but they ended up with about 6 million operating hours. And that was enough to give them a reasonably tight statistical confidence factor. It would have been better if they had gathered more data. You certainly can't do it if we have a very low quantity of valves and you haven't accumulated millions of operating hours. Well, you can do anything you want, but if you do, you'll probably be fooling yourself. Sorry for a negative answer.
How are SD failures relevant?
They're only relevant. A safe, dangerous failure in a single, non-redundant system will cause a trip. In a redundant system, it may or may not, depending on what kind of redundancy you have. So the reason for having any safe failures, undetected or detected, is to calculate and predict the false trip rate. A false trip is really bad in some plants. Maybe it's not bad in your plant, but most end users really would like to have a prediction of not only the functional safety, but on average, how many false trips are we going to get in a particular unit? And if that false trip rate is too high, because false trips are bad and expensive, you can design to optimize that variable as well. The nice thing about our functional safety standard is that is allowed, even encouraged. Optimize your designs.
Those are
Anything
all
else?
I have.
Okay, well, I thank you all for your time. I hope you found the information valuable. If you have any questions or any comments, any ways in which you think this webinar could be improved, please don't hesitate to send us an email. We'll try to get back to you as quick as we can, but our objective is to provide the highest quality training in the world. We need your feedback to do that. Thank you again for your time. Stay tuned for another exida webinar.